Alright, so this unit we're going to kick off talking about chemical bonds. Alright, so really what a chemical bond is, there's really going to be two types. It's a strong attractive force between atoms or ions in a molecular compound. Alright, so last unit we talked all about the periodic table, individual elements. This time we're going to be talking about when those individual elements form bonds. Alright, when they react together to form bonds. Alright, we'll get into chemical reactions in the next unit. Alright, so there's two ways they can occur. One can be transferring electrons, and there's going to be important. There's two types of chemical bonds we're going to talk about. There's a transfer of electrons, meaning one atom gives its electron to another atom, and then they become oppositely charged. Because remember, electrons have that little negative, and that's called an ionic bond. They become ions, is what that's called. When something gains or loses electrons, they become ions, and they form a bond. And then the other one is covalent. They share. All right, so we're going to dive more into that later. I'm not going to spend too much time talking about it now. We'll dive into it later. All right, it's important to know when we talk about compounds, and we've already talked about this. Remember, we talked about a pure substance. You can be an element or a compound. When they bond, we've already talked about this. This shouldn't be anything new. Compounds, the properties aren't anything like the individual elements. Sodium chloride, sodium, shiny metal, chlorine, poisonous gas. When they form a bond, when they react together, they create an edible crystal we put on food. So they're very different. All right, so the properties, so that'll be a question on the test. I'll tell you that right now. When compounds form, the properties are nothing like the individual atoms that make them up. All right, and then you'll also see compounds written as a chemical. You'll see them written as a chemical formula. That tells you, a formula will tell you the elements that make up the compound and the exact number of atoms in each. So like probably the most popular one that everybody knows is H2O. You might have even said H2O without even knowing what the heck you're talking about. You'd be like, H2O, Bobby Boucher or Waterboy or whatever. Gatorade, H2O. H2O is two hydrogen atoms. All right, that two right there, that's a subscript that's attached to the hydrogen atom here, not the oxygen. All right, so that H2O means there's two hydrogen atoms and one oxygen. All right, and when we write formulas, it's very important. The subscript, remember sub like a submarine, a sub is written below. That will tell you the number of atoms there are in that element. If there's no subscript that follows an element, all right, that means that there's only one atom. All right, there's only one atom of that element. All right, so like some of these, like silicon dioxide sand. Si, remember capital S, lowercase I, there's no one there. There's no number there. All right, so I know that there's one silicon bonding with two oxygen. Okay, so if there's no number, that means there's one. Okay, so if there's no subscript present. Now the other thing I'm going to be very particular on is that I have done this a little bit, but when you guys write, I'm going to really start being a stickler on this, because when you guys write your symbols, when you write your formulas, you have to make sure that it's a capital and a lowercase if it's an element, and two capitals if it's two elements. All right. The example here is CO and CO. You might say, well, that's the same thing. This is cobalt, transition metal. This is carbon monoxide. That is very different. All right, that is a deadly gas, very different than cobalt. SiO2, that is sulfur, iodine, and oxygen. This is SiO2, that is silicon dioxide. That's what this is. All right, so writing a capital and writing a lowercase, they're very, very different things. So if you're like, oh, I put SI, and I'm going to say, yeah, but you capitalize it. You're like, oh, that's stupid. Well, I'm like, well, no, you're stupid. No, I won't say that. I would never say that. Well, anyway, I'm digressing. If you write an I, that tells me that is a chemical shorthand for iodine. Capital S is sulfur. All right, so but an S with a lowercase I, that's silicon. All right, so make sure that you do that correctly. All right. Atomic stability. Really, the whole reason why we're going to be doing this is the whole reason why atoms form bonds is to have a full outer shell. They want to be stable. All right. Oppositely charged electrons and protons hold the atom together. Forces cause compounds to form. Almost always the less stable. All right. So stability is reached. Here's going to be our general rule. We're going to try to get to 8. The octet rule. Most atoms form bonds in order to have a full valence shell. that full outer shell of electron. They want to have 8 electrons. Stability. This is what we're looking for right here. Stability. This is what I want you to write down. That is the whole reason why bonds form. To have a full outer shell. To be stable. How do they be stable? Full outer shell of electrons. And a full outer shell is considered 8. Now the only exception to this rule, it's important you might write this down as well, the only exception to the octet rule is that first energy level. Alright, every energy level outside of that we're going to say is filled with 8. But that first energy level, remember, that's filled with 2. Alright, so that's the exception to the octet rule. Those elements have a full outer shell, which is 2. Alright, but basically, the whole point is to be like the noble gases. That's why I kind of skipped through this. Those are stable. They're unusually stable. They don't have to form bonds because they already have a full outer shell. So every element, when they form bonds, they want to be like these noble gases. They want to have that full outer shell. Helium, like I said, it's only got 2 there, but it's got a full outer shell. Alright, because that first level is filled, that first energy level is filled with just 2. Alright, so every element wants to be like it. Alright, we call those the Mr. D of elements. I almost said elephants, that would be weird. Of elements. Everybody wants to be like it. Hydrogen contains 1 electron, it's a lone electron, so it would have a dot just like this. We've already talked about dot diagrams. I'm going to get through this a little bit quicker so we can get moving on. Alright, and so we've talked about dot diagrams. We're going to use these dot diagrams. I might as well go back to it real quick. We put 1 dot around it. That will tell you. So basically, when we do dot diagrams, we want to either have, we either want it to lose its electron, so then the next level's filled, or we want to fill it with 8 around it. Get 8 around it. So we'll talk more about that later, because that's the whole point. All right. And so once again, and this isn't anything. All of these are not stable. They need to be stable. All right, remember, this got 1 in its outer shell. We should know how to find valence electrons. We've already spent the last unit on that. These all have 1. All the elements in group 2, we skipped dip. These all have 3, 4, 5, 6, 7, and then 8. All right. And so these all want to have a full outer shell. So it's no shock that these are going to be more likely to lose their electrons, because look how close they are to having a full outer shell. If it can just lose that 1, then that level's filled. If it could just lose that 1 electron, then this level's filled. Right? So elements on the left-hand side of the periodic table are going to lose electrons, where these are going to gain electrons. These have a very high, it's called electron affinity. These have a very high ionization energy. It takes very little energy to get them. All right, so if lithium can lose that 1, here's an example. Lithium loses that 1. Fluorine will take that in. Then lithium will be full. Fluorine will be filled. But the only difference is that they will now have, the lithium ion will become positive because it's losing a negative charge, which I'll explain that more later. And fluorine will become negative, and those opposite charges will attract. Right, the positive and the negative will attract each other. All right, so they have to achieve stability. So this is what I was talking about earlier. So that can be done by transferring electrons or sharing a pair of electrons. That's what's going on here. So if sodium transfers it, it will now have, sodium has 11 protons. Well, if it loses an electron, it would have 10 electrons. So it would have 11 positive charges, only 10 negative. So it's kind of backwards. We think, oh, I lost something, that's negative. No, it's losing something, but it's positive because the electrons are negative. It's losing a negative charge. So it has 11 positives, 10 negatives, so that this sodium becomes positively charged. Chlorine now has 17 protons. When it gains that electron, it now has 18 electrons, so 18 negative charges, so it becomes slightly negatively charged. All right, and so here's a good way to illustrate that with just the same thing with the dot diagrams. Instead of having to draw the whole shell model out, we're going to use dot diagrams a decent amount. Why I wanted to go over it. All right, so atoms can gain, lose, or share electrons in order to be stable. All right, and chemical bond is a force that holds atoms together. Now, the other thing we want to talk about is counting atoms, because one of the things we're going to have to know how to do is count atoms. All right, so it's really easy. So we would just go through. Remember, so if I asked you to count these ammonium acetate, we would have 1 nitrogen, we would have 4 hydrogen here, and we'd have 3 hydrogen here. So that gives us a total of 7 hydrogen. That gives us 2 carbon and 2 oxygen. So a total of 12. Alright, so when we count atoms, that's going to be just using the subscript to help us count. Alright, and then when you have to use parentheses, then you have to multiply the subscripts. And then sorry, my wife's distracting me. Oh, and an ion is a positively or negatively charged ion. Alright, so that's something we've already talked about as well. Positively or negatively charged atom. And we'll dive more into that when we talk specifically about chemical bonds.